All right, let's dive straight into this explainer and tackle one of the most mind-bending mysteries in the universe. Have you ever wondered why you grow older but never younger? Or why buildings decay over time? Or why ocean waves crash onto beaches, but the beach never, spontaneously launches a perfectly formed wave back out to sea? We experience time as a strict one-way street. It's just a continuous, relentless movement from the known past right into the unknown future. But as we're about to see, the actual rules of the universe make this one-way flow a whole lot more complicated and honestly, infinitely more fascinating than it first appears.
So here's the really fascinating paradox. The foundational equations of physics, we're talking everything from Isaac Newton's laws all the way up to quantum mechanics, they actually work perfectly well backward or forward. There is absolutely no arrow pointing to the future in the math. Think about it. If you were to watch a movie of everyday life played in reverse, like a shattered egg suddenly jumping off the kitchen floor and perfectly reassembling itself on the counter, your intuition would instantly scream that something is deeply, deeply unnatural. Yet mathematically speaking, the laws of motion aren't actually stopping that egg from unbreaking. There's literally no fundamental law of physics that explicitly forbids a reverse flow. So where exactly does this undeniable directionality come from?
Well, the paradox really reveals itself when we contrast the perfectly reversible microscopic world with our everyday, completely irreversible macroscopic reality. Imagine taking a video of two individual microscopic particles colliding. If you play that video backward, you literally cannot tell which way time is running. At that microscopic level, the motion looks perfectly fine either way. The system is entirely time-symmetric. But scale that up to our macroscopic reality, like our egg, which is made of trillions upon trillions of interacting particles, and suddenly the whole process becomes strictly one way. This exact discrepancy between microscopic reversibility and macroscopic irreversibility is what physicists in the 1800s recognized as the arrow of time paradox.
To resolve this crazy paradox, we have to talk about physicist Ludwig Boltzmann and his genius concept of entropy. Boltzmann essentially turned the entire mystery of time into a massive game of probabilities. He realized that the arrow of time isn't something the fundamental laws of motion just put in by hand. Rather, it emerges. It emerges from simply counting how many microscopic ways a system can be arranged so that its macroscopic features still look the exact same to us. Once you start looking at time this way, the mystery of why things happen one way but not the other, it just becomes a question of statistics. It's all about which kinds of states are incredibly rare and which kinds are overwhelmingly typical.
Okay, to really see how this works, let's use a simple counting game of coin tosses. It perfectly proves that macro states are really just combinations of vastly numerous microscopic possibilities. Imagine you toss one fair coin. You get two possible outcomes, right? Heads or tails. Now, imagine throwing 100 coins. Because every single coin's outcome is independent, you multiply those possibilities together. 2 times 2 times 2, 100 times over. What you end up with is an astronomically large number of specific microscopic sequences. But macroscopically, if you're just counting the total number of heads or tails, you'll find that an even 50-50 split can be achieved in a vast, vast number of ways. On the flip side, getting exactly 100 heads can only happen in exactly one way. That 50-50 split, that's your typical high entropy state. The all-head split is an extremely rare, low-entropy state.
And this simple, undeniable math explains exactly why our everyday events don't run in reverse. Think about a spritz of perfume. It naturally spreads through a room like a growing cloud, rather than spontaneously gathering back into one tiny little corner. It's not that gathering back into the corner is physically forbidden by gravity or quantum mechanics. It's just that there are trillions upon trillions of more ways for those perfume molecules to be scattered randomly than perfectly arranged in a corner. The exact same logic applies to mixing two colors of paint, or, you guessed it, dropping that egg. Once that original ordered state is lost, the sheer probability of those particles randomly finding their way back to that exact, highly ordered initial state is effectively zero.
So ultimately, the famous second law of thermodynamics, it's really just statistics in disguise. The future is simply the direction where systems naturally move toward their most typical, high-entropy states. Nothing in Newton's laws or Einstein's equations is actively forcing the entropy up. Rather, as any isolated system evolves, it just becomes overwhelmingly more likely to wander into one of the vastly more numerous messy, disordered states. And our brains, well, we are just hardwired to treat this direction of increasing entropy as normal time.
So we know a broken egg won't unbreak thanks to probability. But let's shift gears for a second. Let's look at how Albert Einstein's theories strictly enforce this causal order across the entire universe.
While entropy explains why systems get messier, special relativity comes in to explain why the fundamental order of cause and effect is completely unbreakable, absolutely no matter where you are or how insanely fast you're traveling.
Right, to understand exactly why effects can never precede their causes, we need to look at how relativity views time. In relativity, different observers moving at different speeds can actually disagree on the timing of events. Sounds crazy, but it's true. However, there is a strict, unbreakable condition that protects causality. If event A happens, and then event B happens later, and the time difference between them is greater than the time it takes light to travel the physical distance between them, they are separated by what physicists call a time-like interval. Because a signal traveling at or below the speed of light could physically get from point A to point B, event A genuinely has the potential to cause event B.
And it's this exact concept of a time-like interval that firmly anchors causality for us. For time-like events, the cause absolutely must precede the effect, no matter how incredibly fast an observer happens to be moving. Let's say a person throws a rock, and a moment later, a window 10 meters away shatters. The time between those two events is much larger than the fraction of a nanosecond it takes light to cover those 10 meters. Because of this time-like separation, Einstein's math guarantees that there is absolutely no perspective in the universe, no zooming spaceship, no bizarre alternate reference frame where someone would see that window shatter before the rock was thrown. The causal arrow of time is totally locked in. It's why you can never be born before your parents.
But on the flip side, we have space-like events. These might actually swap order depending on your perspective, but here's the catch. They can never, ever influence each other. If two events happen so far apart and so close together in time that not even light could travel between them, they're space-like. In this scenario, one observer standing still might see event A happen first, while someone flying by in a spaceship might swear event B happened first. But because they are completely disconnected, neither event could possibly send a signal fast enough to cause the other. This weird time swapping doesn't violate our physical arrow of time at all. Causal relationships remain strictly a one-way street.
Now for a quick glimpse into some really advanced physics at play, there are newer theoretical models showing how irreversible temporal evolution can even be viewed geometrically. There's this fascinating framework called the TAP model, which stands for thermodynamic asymmetry from projection. It essentially suggests that the arrow of time emerges when highly complex, high-dimensional information is projected down onto our lower-dimensional reality. Think of it like trying to play a massive, uncompressed 4K video file on a really old, low-resolution monitor. The screen simply doesn't have the capacity to display all that information, so a ton of data is lost in the projection. According to this model, entropy isn't just about statistics, it's this exact structural mismatch. Once that original, complex information is filtered out and lost, it creates an irreversible update. You can't uncompress the file and get the original back. And that gives us a deeply fundamental, geometric arrow of time.
Okay, so if we take this idea of constantly increasing entropy and scale it all the way out to the cosmos, to the very beginning of reality itself, things get even more profound. We've established that entropy is always increasing, right? We're moving from ordered, rare states to messy, typical ones. But wait, if the universe is more disordered today than it was yesterday, and it was more disordered yesterday than 1 billion years ago, well, logic demands that we trace that arrow all the way back to the start. And that logic tells us that without a finely tuned, incredibly low entropy beginning, we wouldn't have an arrow of time at all. In his book The Big Picture, physicist Sean M. Carroll points out something amazing. Our entire sense of forward and backward in time is due entirely to our relative proximity to the Big Bang. The early universe absolutely had to be in a state of supreme delicate order. Think about it. If it had started out as a totally messy, high-entropy soup, already at thermal equilibrium, there would be nowhere for the entropy to go. Nothing would happen. No stars would form, no planets would gather, and time as a directed experiential flow? It simply wouldn't exist. And the odds of that happening are truly staggering. The number you get when physicists calculate the entropy of the early universe by looking at the cosmic microwave background radiation is mind-blowing. They find the universe was uniquely, incredibly low in entropy. To get a starting condition this finely balanced by mere random chance, the odds are roughly 1 in 10 to the power of 10 to the power of 123. That double exponent is a number so ridiculously large that if you tried to write it out by putting a 0 in every single proton and neutron in the entire observable universe, you would run out of particles before you even made a dent. It is the ultimate low-entropy anchor from which all of our cosmic history has been flowing ever since. So, I'll leave you to marvel at that incredibly provocative thought. Every ticking clock,
every single memory you hold, and yes, every shattered egg, it is all just the universe slowly, inevitably settling into its most typical state. Our psychological arrow of time, the very fact that we can remember the past and take action to change the future, is a direct consequence of this massive thermodynamic slide. We are all essentially surfing a grand cosmic wave that started billions of years ago at the Big Bang and is slowly spreading out, mixing up, and winding down. And honestly, it's exactly what gives our lives consequence, direction, and causality. Thanks so much for joining me to explore the arrow of time.